Надеюсь, вы все в курсе, что у нас был небольшой конкурс, он все еще в процессе. В течение сегодняшнего для меня сумасшедшего дня меня смогли найти несколько человек. Трое из них первые делят пьедестал, так сказать. Если вы позволите, я вас отниму несколько минут, и ребятам все это вручу торжественно. Будьте здоровы. Ребят, кто ко мне подходил, я сказал, что у вас третье место. Бегом, бегом! Третье место. Вот эта замечательная футболка C++ Russia. Так, поздравляю. Второе место, ребят, кто у нас? Какой у тебя размер? Какой размер? Отлично. Второе место. Замечательная футболка C++ Russia. И вот такой вот суперский плакат, который называется «Карта C++». И более того, я сейчас попрошу Андрея. Андрей, will you be so kind to sign this?
I'll be happy to sign.
Yeah, you can just use me as you want.
A wall?
Yeah.
Okay.
As you want.
Hold it this way. All right. Okay, where's my territory here? Oh, there it is. Low key.
Yeah,
Okay.
yeah.
Awesome.
Thank you.
Thank you.
И первое место. Человек, быстрее всех нашедший меня со всеми печатями, получает эту замечательную футболку C++ Russia. Вот эту супер классную худи C++ Russia. И эту потрясающую карту с автографом, вы знаете кого.
Awesome.
He asked to,
He doesn't want it on the face.
because he wanna sell it on eBay, yeah, sure.
Don't spoil the chart.
Ребят, меня очень много спрашивали о том, будет
you.
ли Андрей подписывать что-нибудь.
Good to meet you.
Ну, в общем, Андрей очень клевый. Он говорит, что он с удовольствием подпишет все, что угодно на всех частях вашего тела, если вы этого хотите. Вот. И все это будет после его доклада в зоне кофе-брейка. Только, пожалуйста, давайте мы самоорганизуемся, не будем его со всех сторон обступать, а аккуратно очередь выстроимся и попросим что-нибудь подписать, книжку или программку или еще что-нибудь. Хорошо? So, the closing keynotes, Andrei.
Thank
your
you.
word.
Thanks. So I heard Andrei and then stuff, and then everybody laughed. And then пожалуйста, which is, I understand, like, please, right? So my interpretation is like, this jerkwad and Andrei is going to give a talk, and everybody laughed. And then he was like, please, give him a chance. So, all right, so I'm operating on a key assumption here. I don't speak Russian, but I do have one key asset, which is I have the standard Eastern European accent. And my assumption is that you're going to have an easier time understanding me than those native English speakers. Come on, right? Is this better than? Okay, thank you. Yeah, this is awesome. Okay. Announcement number 2 is the description you saw online. No, that's not going to happen. It's going to be an unexpected theme, which is the expected pun present. So I'm going to talk about something completely different than fastware, which I'm going to talk about at the .next conference, which is like just 2 days from now. And Sergey and I chose this topic because it's closer to C++ and standardization and standard library, so we thought it might be of high interest. So here's what happens. True story. I have a Wikipedia page. I'm not kidding. I never contributed to anything of it. So there's a Wikipedia. If you search me, I'm there. And there's essentially like it's contest. There's people who say, who's this guy? It doesn't deserve a Wikipedia page. So it's kind of in this kind of a weird status, which is like this page is being disputed and whatever. So anyhow, so probably to improve the situation, somebody, I have no idea who, deleted everything I ever did and put Andrei Alexandrescu, came with the idea of expected. So that's my lifetime work is expected, right? So here goes, right? So here's the idea. We're going to talk about errors. I'm going to talk about errors. And we're going to talk about exceptions. By round of applause, who likes exceptions? Come on, by round of applause, come on. Who likes exception? Yes. All right, who doesn't? Who hates exceptions? All right. That sounds like I like stoplights, but only when they're green, right? When they're red, I don't like them. Okay, so exceptions have kind of a tricky story. There's been quite a bit of history to them. And most of us sort of start our careers when exceptions already had been invented. So most of us took them like non-critically. They said, this is kind of feature, let's use it. And I remember when I first learned about exceptions, all of my functions had a try-catch in them. Like, and then when I learned about templates, all of my functions, everything I wrote had a template in it. Unfortunately, that scar didn't disappear. So I still write things whenever I can with template in it, but not with try and catch anymore. So what would be what do you compare exceptions against would be a question for us today. What were exceptions designed for? What was the purpose? How are they best used? And I submit that not a lot of us have a very thorough understanding of what would be the best, most principled way of using exceptions. So what are the consequences the new setup that the existence of exceptions creates, and how do you write code playing on their strengths? So actually, sometimes it's good to have error codes because one guy's unique situation is another guy's current, very frequent case. For example, when you work with networking, expect bad things to happen when you network and you expect to retry and things. So maybe exceptions are not the best response to that scenario, right? In other applications, maybe you have a highly available system in which all of these networking errors are taken care of and retried automatically and that kind of stuff. So, it's not really clear when you should and when you shouldn't use exceptions. So I know what we want from exceptions. We want everything and we want to pay nothing for it. As it goes, we want to learn them once and use many times. We want to minimize what's called soft errors and maximize hard errors and avoid the metastable states. This kind of, it's a term from reliability. So what is a soft error and what is a hard error? Non-rhetorical question, I'm actually asking you. Raise your hand and shout loudly in Russian if you please. Yes, please. A soft error you could recover from, a hard error you cannot. Actually, that's not the case. It's a nice definition, but it's not sort of the commonly used definition. Other thoughts? Well, a soft error is you don't immediately recognize it. It's an error, but the consequence is not visible yet. A hard error is like the system stops working exactly when the error happens. What would be an example of a soft error? And I guarantee everybody in this room, I guarantee all the people not in this room have had such bugs, soft errors. We don't, we're cool. Like everybody not here has had such errors. Like the soft errors are like you dangle a pointer, right? Does the program fail immediately? It may or may not, right? So this kind of a soft error. So dangling pointers, you take the address of a local, escape it somewhere, and that kind of stuff. So you want to not have those soft errors, and you want to have errors that are immediately recognizable as soon as they happen. All right. By the way, so from where I am, I hear like a lot of echo. Is this like, I can't hear myself thinking. Do you guys hear me okay? Is this? Okay, so it's only me who's hurting in this room right now. All right, so we want to also benefit of local handling because not always the library can decide where to handle the error. We want to, this is interesting and important, we want to transport an arbitrary amount of information from wherever the error happens to wherever the error is handled. We want to have a small cost on the normal path, and we want to make correct codes easy to write and consequently incorrect code difficult to write. So this would be kind of a nice laundry list of things we want from a nice error handling system, not necessarily exceptions or whatnot. Let's start with a good example of a poorly designed library function, which is now kind of widely avoided by people who write serious applications. What happens if A2I encounters an error? It returns 0, which is like the most useful, the most frequent number ever in any program, right? Did you know most numbers are 0 and most strings are? Most strings are? No, they're not empty. They're C++ Russia, right? With Cyrillic characters. Most strings are empty, right? So most integers are 0, so such a frequent value is inappropriate for encoding errors. What would be a good value to encode the error of A2I? By the way, if you wanted to choose an integer to sacrifice on the altar of correctness, what would that be? Max int, none, there's no none. All the bits are valid in an integer, right? I would choose probably the smallest integer possible. Because that's it's actually weird because minus that guy is the guy, so it's not positive. So it's kind of quite a peculiar value to start with, so the hell with that guy, right? So, all right. So then, let's say A2I does return 0, so now we want to write a small routine that figures out whether the number was 0 or not. Actually, it's not that easy because it's got to recognize a 0, but also a space followed by a 0, a tab or a new line, or several. It's got a space followed by plus by many zeros, and etc. All of these are valid zeros. So to let me make this clear. To make sure that A2I failed, you got to write a little A2I. It's as complex as writing your own because it's like 5 lines, right? So not a nice way of handling errors, right? Not a nice way of dealing with things to return a frequent value, right? And this has to do with the fact that A2I is what they call a surjective function in math. Who can tell us what the surjective function is in math? Russia has a huge, long tradition in mathematics, right? Come on, you know. And France too, right? So the French guy knows. So come on, Russia, give it, come on. Yes, loud. No, it doesn't map different values to different outputs, that's injection. Covers all the target domain. Covers the entire code domain. For every value in the code domain, there's at least one value in the domain. That is an injection. It's and if it's an injection and a surjection, it is a bijection, hypodermic bijection. That's right, friends. Great. That was a joke. No matter how bad it is, I'm going to keep on doing it. All right. So this is kind of a difficult counterexample of returning an error by means of a unique value. So let's get to the good old Erno. And actually, the etymology of the word is kind of nice, right? Because it means no, it didn't work, right? Did this function work? No, it didn't work. So that's the origin of the word, and it's general because you can encode any error in the Erno. It minimizes soft errors, no way, because how many of you check Erno every time after you call printf? No, yeah, that's right. No, that's the perfect response. It does allow for centralized handling. You do many things and then you check Erno and say, oh, something bad happened at some point. I don't know when, but then we can do local handling. We just check Erno after every call. We can't, however, pass arbitrary amount of error information. And this is like, Erno has these little encodings in that integer that they put and all that stuff. So it has an enumerated range of values and stuff. So it's kind of awkward. It does have little cost on the normal path. Everything the error path has to do is just set that global. Actually, I lie. It's not a global. You know the story of Erno? So Erno started as a global, and it can't be a global. Why? Threads, thank you. So each thread may have a different error state. So Erno became from global, it became a? No. macro, right? Because every good thing must end in a macro, right? So it became from a macro that in turn, calls a function that gives you the whatever for the current thread. So there's a story to it, right? So unpleasant. It doesn't make correct code easy to write and that kind of stuff. Great. So Erno, too much red on the slide, right? Too much red. We don't like Erno. All right. How about returning a special value, which we just talked about in the context of A2I? It doesn't work with surjective functions. We just discussed that. It does not minimize soft errors because you may still continue to work with the wrong value. And I'll give you an example with when I was doing neural networks for my PhD thesis. I was working. I had a bug, right? Like all of you had bugs. Come on, right? Don't look at me like that, right? Don't start with the crying right now. Come on. So I had a bug, and the bug made the float value become a nan, not a number. And in that particular generation of CPUs, I don't think all CPUs have the same behavior, but it turns out for certain CPUs, whenever you input nans to additional processing functions, they're going to run a lot slower. So doing anything with a nan was very slow on that particular CPU. It was kind of one of the Intel models, in 2009, 2008. So that made, didn't anybody encounter this kind of stuff? It's just much slower with nans, much slower with nans. So I was like running my neural network, and then you have like a decider which says like it's greater than 0, less than or equal to 0, and it was making always the same decision, and it would recognize by chance whatever % of the data. And I was like, oh, this neural network is doing some good work because look, it takes so long. It takes a long time to do all that processing. So it took me a while to realize that actually it was just simply propagating these nans. So that's not good, right? You still can proceed with the wrong values there. Centralized handling is difficult because you simply just return a special value. Local handling, this is pretty much the only major advantage here. You can't pass an arbitrary amount of error information. Well, it may or may not have a little cost on the normal path. And it makes correct code not too easy to write. So that doesn't make us happy either. How about like a function like string to long in the C standard library? It takes a double pointer to character, which is like it's going to fill that pointer to a pointer with a pointer to the last error that it saw. Right? So if it's not, it's going to put a null in there. But if there's an error, it's going to tell you exactly where the error was. So functionally speaking, it's an informative function. So it tells you exactly where the conversion couldn't work anymore, right? But just making one call to str2l takes like 5 lines of code, like an idiot, right? We don't like that. That's kind of unpleasant. So it doesn't, doesn't really make correct code that easy to write and that pleasant to write. So that we have some trouble here, right? And it's very local, so whenever you have the error, you have to handle it immediately. So that also makes us unhappy. We are one demanding bunch, aren't we, folks? We are one demanding bunch. So, well, how about exceptions? By necessity, we get to the notion that, hey, we want to have something like the following, which is good old A2I, but it shouldn't return an integer. It should return some sort of I'm inventing syntax here. This is not real code. Just to illustrate the idea, I want to return the whole, an int or something happened, right? And something happened is like an invalid input. It's its own type, its own thing. And inside the invalid input can tell you what happened. Actually, when you do A2I, it's not only that you can have the wrong conversion, but you may have an overflow. It may be a number that is valid, but is too large to fit in an int, right? So several cases may happen while you convert things. So we want to have this guy, and we want to do some sort of a type switch thing, like some languages allow you to say, oh, was it an int? Then I'm going to do the normal path, the happy case, and this is the unhappy case, and that's how it goes. So hat tip to algebraic types. This is a sum type. It's pretty well known. It's a classic in theoretical computer science. Nothing really out of the ordinary here except for the invented syntax. So notice that this is not, how should I put it? I'm not inventing this or proposing this, or this is not smart. It's not clever. It is the norm. It is the next, the obvious, the least resistance thing. You want, whenever you do a conversion, you want to get an int or something happened and you couldn't get that int, and here's why. So once you start pulling that string, you don't discover anything. You just by simply following the logic, you're gonna get there, right? And continuing with the logic, we want to actually give different roles to these things, because we want the integer to be expected, because this is a happy case. Look at this. I'm going one slide before. So in this syntax here, I'm giving equal importance to the integer and the invalid input. But actually, they shouldn't be given equal priority, because in 99% of the cases, the int is going to be the case. So I'm going to say, well, I expect an integer, and I don't expect, but it may happen that I get an invalid input. Right? So we have the overt, the visible, the main, the happy case type is integer, and the covert just slid under the rug somewhere, like, in the background, there's going to be the unexpected case, right? So we have the local code should be able to simply don't care about invalid input. So whenever you want to code just for the happy cases, just go through and use that thing as an integer. So function in general has an overt return type plus one or more covert return types. And this is really just, again, by following the path of least resistance. We want a nice error handling system, so that's what we get. And obviously the next question would be, okay, what happens to those guys in the shadows? What happens to the unexpected case, the unhappy, rare case? So where should those guys go? Well, returns values of a function, they should have their own stack, and they should have their own handlers. That means try and catch. And we just, ladies and gentlemen, we just reinvented exceptions. I mean, really, we really took like the logical chain of events, of necessities, as it were. And I'm like, crap, I'm back to try and catch. Right? That was like, everybody's like, oh yes, that's so funny. Okay, great. I'm gonna raise my left hand whenever it's a joke. I'm gonna raise my right hand whenever I want everybody to stay silent, like right now. Okay, great. So, well, we have the covert exception pass. We have the colors must return, plan return types, all that stuff. And there's something peculiar about exceptions, which comes from this as well, which is the following. In general, do you consider C++ to be a first match language or a best match language? The language rules. Just shout. Yes, please, shout. Huh? You gotta, like 10 times louder. First, the best match? And it's the best, right? Best match, come on. Best match or first match? Yeah, so except for exceptions, it's best match. And let me explain what I mean by C++ being a best match language. Whenever you have virtual functions and overriding, which match is going to be chosen? Best match. Whenever you have overloading, best match. Whenever you have template pattern matching, yeah, stay with the exceptions. Wait, you're ahead. Whenever you have template pattern matching, best match, right? Whenever you have exceptions, trap, warning, that's a trap. It's a trap, right? So whenever I have exceptions, it's actually weird. It's first match. And it's the only place in which the C++ language is first match, right? And this comes from the fact that you got to plant your own return type. And having the return stack first comes before type. So that's why you need first match and not best match. So this it just makes things a bit odd. But it's, by the way, you should know that there are perfectly valid good languages in which They go with first match everywhere. Examples. Huh? Ask all functional languages. First match. There's debates out there about whether first match is better than best match. Hey, best match. I mean, it's in the name, man. Come on. What's with the first match? So in a function language, the order in which you write the specialization of functions, that's the order tried. It's a linear search. So essentially, C++ is first match for exceptions. So, and it's based on types after that. Great, so we just invented exceptions. So here we go. And we have a red line here. And what's that like the, so the make correct code easy to write. In 1998, everybody's like, yes, exceptions, man, they rule. In 2008, people were like, I don't like exceptions. And right now, it's like, maybe they have a chance, right? Maybe they have a chance. So there's new primitives in the language, and a bit of a few improvements to the language as to regards exceptions. So here today, we're going to focus on this red thing because it's important. You want to sometimes handle exceptions locally, right? All right. So the worst things with exceptions is that the user must ensure transaction semantics of their own. And for that, we have the beautiful RAI idiom, and we have things like scope guard and stuff. I'm not sure if you know about this, but if you Google for it, there's like the first match is for like it's for a gun. It's a scope guard that protects the scope of what's the name? Zaitsev, the guy with the right, the hero with the sniper, right? For sniping guns, that's the first match. Forget that. The second match is my article on scope guard, right? So it's how to actually execute code after that. And actually, so this has a lifetime of its own because people are adding to the standard some facilities to allow people to work with scope guard. Great. Local error handling with exceptions is kind of unpleasant because you got to write the try and the catch and all that nonsense. So it's kind of a bulky proposition, and they're hard to analyze. This is kind of a classic topic by now. I don't need to insist on it. Actually, I should because there's this funny thing. Who's read Herb Sutter Exceptional C++ series? Okay, everybody should. Everybody, folks, they're like available online. So his exceptional C++ series includes an example that has like 2 lines. It's like identify all the exit points from this function. And there's like 17. It's like amazing. That little function could end in 17 different places. So because of exceptions and stuff, right? So it's amazing. So too many paths. And odd semantics, composition with exception is difficult. You can't have more than one exception in flight except when you can. Right? That kind of stuff, right? Great. So today we're going to do the following. So by the way, congratulations. We're just starting right now the talk. This is where the material is starting. Until now it was all just by means of background and introduction. So we're going to do local handling today, and we're going to minimize software, so I'm going to make correct code easier to write. But first, let me start with a couple of background items. Who knows about STD variant? STD variant, boost variant, friends? Great, thank you. Visual basic variant? Anyone? All right. So that's essentially like one of those types that is a sum type in theory, right? They call it because you can encode all of the values of type number 1 and all of the values of type number 2, and that's how it works. How do you typically implement a variant? Shout. Yes, real hard, shout. And how do you gotta have a bool. So what I need to hear is union and bool. Did I hear that? Yes, union and bool. This is like the secret of like having like a variant of 2 arms, which is sort of the basis of everything. You have a union and a bool. And thank you, Lois Goldwaite, for making union usable. Because before C++ 11, union was restricted to types without constructors and without destructors and that nonsense. It was practically impossible to use intelligently. So Lois said, there's something real bad here. So let's make union a simple a simple way to paint layout. Paint layout. So, you put a union there, and essentially you say these guys are going to be just inert data at this address, which is an amazing kind of thing at low level because it allows you to do really interesting things with layout. By the way, John Kalb mentioned this morning, like Java and all of that competition between C++ and Java in the early 2000s. And, pound for pound, there's a lot of Java code that, for example, operates on arrays of double. And with the current optimizations, it does as well as C. So if you choose your code carefully and have the wind from behind, you're going to get C-like performance in Java, right? But where C++ still has an important advantage is its ability to control layout. Layout is where it's at when you optimize. So people, architects, spend a lot of time on designing data such that the layout is as compact and as good as possible. For example, you want to put the hot data at the beginning of the object, right? You sort the data by hotness. You go to hotornot.com or whatever, right? You sort the most beautiful data comes at the beginning of the object, and the ugly data goes at the end. Right, that's how it works. And then, you want to pack as much as you can in that first cache line, in the first 64 bytes. Right, so that's why people do unions and that kind of stuff, because they want to pack as much information as possible in that little space there. So once you have that, you're going to have a very rapid, a very fast data structure. That was a parenthesis. So getting back to our background technology, so we have these variants here. And we have std optional, which is optional. It's either this guy or nothing. Pointer. What? Void pointer. Unique pointer. I hear these things. I have no idea what you guys mean. But I'm going to just go in the hope that I didn't make a fatal mistake. So essentially optional means it's either an int or there's nothing. And that means really packing an integer and a bool together. Think in terms of layout, right? Think in terms of like what the data structure looks like. I want everything in an integer, but I also want the opportunity to say it was nothing like that. It was not an integer. So that's at least kind of information-wise, it's an integer plus 1 bit of information, right? So that's optional. But I don't want variant because variant gives equal importance to both. I don't want optional because I want their information. See where I'm going with this? So we also have like things like the maybe either monads, which also don't have, have similar properties with these guys. So this whole technology, this entire technology is very close to what I need here, which I'm going to illustrate next. There's a related work in C++11, promise and future, but those are oriented toward threads. But they do embed a fundamental idea. These types pack either a T or an exception. That's where we're going. We're going to a type that packs a T or an exception. And the meaning is this object is either a T or the exception that prevented its existence. Right? See what I'm saying? So it's either I have the money or I have the gun. Right? Okay, so it's one of these. And we want we don't like the threads aspects and everything. We want something like really. All right, so union types we discussed already. I'm not going to insist on this because it's pretty simple. Boost, variant, whatever. So in the simplest form, it's either, and you have a T and a U, and have a union, and you have a T or a U, and you have the Boolean. Case closed, right? Great. Now with expected, we want the following. We want to define expected of T and E. And T is the good guy and E is the exception, right? And our idea is to express this union of a overtype and covert type, over being the nice, frequent case, cover being the unexpected case. And the normal case would be just the overtype is there. And in the wrong case, we have an E. And E has any amounts of information about what happened. Notice that when I produce the subject, the exception has not been thrown yet. It exists, but it hasn't been thrown. Why is this important? Yes, please. We can handle it locally, so no need for trying and catch and all that nonsense, yes. And there's one more effect which may seem secondary, but it's very important for people who care about efficiency. Right? Yeah, I don't do all the stack unwinding, all that nonsense, right? So you can actually mark the function as it's not going no except. And like people, we had so many keywords about exceptions. Like we have try, catch, throw, and we have no throw. We have throw nothing in the signature, which by the way was deprecated, right? You know that. You don't. If you didn't know about it, you're good, because it was deprecated. That was a great joke. What, guys? What's anyhow? So and now we have no except, which is different from throw nothing. And no except is actually introduced by people who care about efficiency, because it means take me on faith, this function is not going to throw an exception. And what happens in that case, the compiler is not going to generate the bulky prologue and epilogue code for the case in which an exception may be thrown, and the function is much more compact. You're looking at 7% improvement potential in efficiency. I just measured on a large application, it's on average. But 7% can be significant if you're looking at high traffic. So, and I'm saying like just turning a switch on and off. It's not something like you don't rewrite your code. You just get 7% just like that. So it's quite impressive, right? So you don't want to throw the exception. All right. So the exception is eagerly constructed and lazily thrown. This is the secret, right? We want to have that ingredient. So an expected T E is either a T or an explanation E on why the T could not be produced. Right? Either have the homework or the dog that ate the homework. Right? Great. So this is very nice now, because we can have an expected, look at the signature. It already tells you what you should be doing. Right? I expect an integer or an error. And then it's A to I and whatever. And if it returns an integer, it's, whatever. So then we're like, can say, oh, does the result has result has value? It means an integer is there. Or I can get the error and I get the error. So it's very easy to say, use an idiom like if result, use star result. At this point, I got to say, we're going to migrate a bit from our initial assumption into an interesting discussion. Star result. That makes result look like a pointer, right? But it's not a pointer. It's really just one of those expected things. And even more so, I actually test if result. I test result as if it's a pointer against null. So what's happening here? Well, this is what happens. This was not my initial idea. I said, just use the, there's no smart pointer stuff. A gentleman by the name of Jean-François Bastien, he took my idea and he made it into a proposal for C++ 20. So please note, this talk is not completely useless to you, because you may have an interesting career in 2020 in which you get to use this kind of stuff, right? So this guy took it to committee for a proposal, and they said, we like it, but we don't like the interface. We would like it to be more like a smart pointer. We like the idea of making this expected thing behave a bit like a pointer. So you put star there to dereference, and you put you test it against null, and you kind of do all these pointer E things. Even you can do the arrow. You say result arrow method and that kind of stuff. I'm not a fan, but I'm not a hater either. I'm neutral. Switzerland, right? So what do I care? It's a nice idiom. Let's give it that. A question to everybody: what happens if I use star result and the integer is not there? That exception will be finally thrown. Yes, thank you very much. It's lazily thrown, right? It's going to be thrown. Great. If you want centralized, you just don't care. Just use star result with impunity, and it's going to behave just as a function with exception. So nobody cares. Great. All right. So now let's see. Let's see the high-level view of this expected type. It took us to a nice point in design space. It took us to a point where we can associate errors with computational goals. So it's all in the same, under the same umbrella. You have a type that expresses, I have this computational goal, which is I want to compute an integer, string, whatever result I have, and there are these contingencies that may happen. Naturally allows multiple exceptions in flight. This is even more interesting. What do I mean by that? Normally, how many exceptions can you have in flight in C++? One per thread. As many as you want. Per thread? As many as you want per thread. Actually, not to kid, it's a long discussion because all of you are right. Because in a sense, it's only one, but in another sense, you know the story with the unquote exception and the 7 dwarfs, right? You can have an unquote, you call unquote exception, it returns false, but in fact, there's still an exception in flight and vice versa. So it's not really that easy to discuss how many exceptions can you have in flight in C++. In the catch block of a try statement, the exception that has been thrown is not yet considered a handle. So in a sense, it's still in flight. And if you throw inside that catch block, you're going to have like 3 exceptions coexisting without the program terminating, which may be a surprise to the novice, right? So that's kind of unpleasant. So with this approach, it's easy because exceptions are not thrown. You can just save them for later and use them later. Just accumulate. You can have an array of them. Right? You can have a hash table if you want. There's no limits, friends. You can't put in a file. Sorry. I was like getting ahead of myself here. You can with the nice, the interpreter from the last talk, you could do something like that because you serialize them. So, this kind of stuff. That's very nice. You can teleport them easily and naturally across threads. Right? No problem. Across thread boundaries, no throw subsystem boundaries. This is important for interfacing with C, for example, and other languages. You can across time, you can save them now and throw them later. You can do anything you want, right? Combine, group, collect. So this is kind of a nice, it's a nice point in design space, and I'm very happy that Jean-Francois took this idea to the committee. So let's actually implement it. There's a lot of detail to it, but in essence, we're looking at the union plus bool, yes? And it takes a bit of finesse in implementation, but you guys know, right? First of all, like for example, a default constructed, I'm going to turn the slide off. A default constructed, this is a trick question. Default constructed expected. What should it be? Good or bad? This side says bad. This side? Bad. Oh, everybody's. Okay, well, Slavic soul, huh? You're negative. You're kind of pessimistic here. Dostoevsky, guys. Come on. Be more happy. Default expected. I'm not saying default whatever. I'm saying default expected. By default, the constructed expected is going to be good. It's the default value of the good type. Did I mention that we have an overt type, which is like the default whatever, and the covert type, which is the bad thing? The bad thing is rare, exceptional, infrequent, pessimistic, depressive, right? On lithium, right? It's bad. Unhappy. But the default case is the happy case because we want to behave like the happy case most of the time. That's the frequent case, hopefully, right? For us all. So we want to make the default constructor a yay. So I'm going to place my new a tin inside yay, at the address of yay. Yeah? Great. If I construct with an explicit value, definitely I'm going to construct that guy. And then, essentially like for every of these I'm writing, there's like a few more. With the R value and with the constant value and the non-constant value and with all that good stuff, right? So this is kind of really a third version of the thing. It's amazing. Looking at the proposal, it's amazing just how much code is needed. But essentially, you get the idea, right? I'm going to copy construct this thing here. So now I have a weird thing here. expected constructor, but I don't take a E. I don't take a const reference to E. I take another type, which is unexpected of E, RHS. And this solves a design issue. And you'll tell me what the design issue is, friends. You will think right now in real time and let me know what the problem is. Why do I need another wrapper type on top of the exception? Sorry? Excellent. T and E may not even be the same, but they may be convertible to each other. What if I want to have an expected of stood exception? I expect an exception right now. Right? I could. Or what if I want to express the exceptional case as an int, and I expect an int or an error which is also an int. Or I expect a double or an integer, which is, and then there's convertibility, and it's kind of it gets really, really weird, right? So, the solution here is the following. Let's add one very simple wrapper type. It's only 1,000 lines. Really simple wrapper type on top of which is going to be unexpected. It converts. It's just simply a do-nothing wrapper, but it encodes the notion that I want to construct this exceptional case. So it says unexpected. Now, there's still a limitation. I cannot expect an unexpected. You get my drift? I can't write expect and then the first argument to expect is unexpected int. That's still a limitation. And if you take it to it's infinite regression, you can never solve that problem entirely, right? Because then you add one more type and it goes forever. So this is a limitation in design. You can't expect the unexpected. It's a nice catchy phrase, right? Come on. Sounds like a detective book. Don't expect the unexpected. Mannix, that kind of stuff. Great. So with the limitation, we proceed with the simple wrapper type unexpected on top of anything. And then OK is going to be initialized to false. And notice that this is really like bool OK equals true. It's sort of a grammatical, like I'm being a smart aleck here. Because grammatically, I'm setting myself up for happiness. I'm saying bool OK equals true. So by default, everything is dandy. Right? If I don't do anything, it's going to be good. Right? If I don't care, it's all going to be okay. Right? This is this is like the happy line, right, in this code. So then whenever something's not okay, I need to initialize it with false, and I need to be careful to propagate it, right? So then I get the value from RHS. This would be fetching the value from there. And again, there's a few overloads here. We have the forwarding constructor, that kind of stuff. Okay, great. So these would be the copy constructor and the move constructor. And I initialize OK, and then I'm going to initialize the appropriate field in the union. And same here, right? With move and everything. So notice how depending on what's in the source, I'm going to carefully copy the source into the destination and move it as it were. So these need to be written by hand, because at this point with union, you got to do it by hand, because union is not automatic at all, right? All right, so then we have the promised pointer operations. We have operator star, and if it's not okay, throw nay, return A. Oh, this is like the code writes itself, ladies and gentlemen. This is awesome, right? It's only you can read it. If not okay, throw nay. All right, so then we have the corresponding const operators and the move operators and everything, the R value operators, and which have the same body. And here we have the arrow operator with the const version. There's nothing really super creative here. Let me think for a second. Oh, this is the accessor for the error. And note that, if I'm accessing the error without actually there being an error, it's going to be an undefined behavior. Right? And here there's a discussion right now in the committee. People say sometimes you should throw unexpected query of unexpected. Right? There's an exception that they discuss adding, which would be thrown in the case you want to access the error when actually, no, actually it was good, friend. I mean, what's happening with you, right? What's wrong with you? All right, so we have the error and stuff, and we have the accessor for value. And of course, with the accessor for value, we know what happens if you have an exception. And you have the explicit operator bool, so you do if. These are nothing to write home about. These are easy. Oh, and there's value or. Value or, what does it do? Yes? Yeah, or this guy. Yeah, don't throw. So return either the value or this guy. Right? So it's sort of a nice version of value of give me the value or else give me a default. So that's nice to have too. The most interesting function, this I wanted to really get here. The most interesting function is swap. And actually I found bugs in the implementation proposed for standardization. I wrote the guys and I said, oh, actually there's a bug in there. So, okay, great. So here's what happens. When you try to swap two of these union things with booleans, let me handle the easy cases first. If both are okay, then I just gotta swap the yays. Yes? I swap the good things. Right? Okay. Otherwise, another easy case. Here I'm just saving myself work. I swap the arguments in the call to swap. You see my point? All right. So this is slightly inefficient because I'm going to test again things that I tested already, but it fits on a slide. So that's an important constraint for optimization. That was a joke. All right. So this is not interesting. It's just swaps because I get here. So here's the another uninteresting case. It's not okay and RHS is not okay. Both are bad. I swap the nays. Case closed. Right? And here comes the not easy part. Right? The ... Well, the hard part of swap looks like this. All right. So I'm bad. The other guy is good. Right? Well, here's what I'm going to do. I'm going to construct on the stack a temporary by moving it from nay on the stack. I move from my nay. So this is my bad case. Now I can destroy my bad case. Right? Remember, after a move, the source is destructible. So I'm allowed to do this. Yes? All right. Now I have, like my space has been emptied. Right? My yay and nay union is now empty for receipt of anything I want. Right? So now I'm going to construct at A, I'm going to construct a T of std move RHS.A. Yay. Right? Okay. At this point, I set OK to true, and from here down, my object is correct. I need to fill RHS. So I'm going to fill RHS from the stack by destroying its yay and filling its nay. That's a head scratcher, isn't it? Oh, it's not? Okay, it's easy for you guys. Okay, awesome. So now, okay. So tell me in which cases this code can fail. Yes. If the move constructor of this guy throws, or the first one, bad juju, right? Not good. We don't like that, right? That's why you can't implement this function unless the types are, has no throw move constructor, which is a trait in the standard. So you need to limit the workings of this swap function to those types. Otherwise, you can't implement it, which is an interesting, odd situation to have. And it's not easy to discover because people write code and it's like, oh, this looks plausible, this looks good, but oh, wait a second, what if that throws an exception? And in that case, you're all unable to write your code properly. All right, so let's get on to some typical uses. I've expected double or runtime error, good equals 100. This was going to make a double, that is totally fine. Assert start good is 100, it's going to pass through. Unexpected disambiguous, the bad case, as we discussed. So I'm going to say expected bad equals unexpected runtime error. Sorry, there's a There's a parenthesis here. Apologies about that. Please add it to your hard copies on paper, which there's none. There's no, right? There's none. Okay. Add it mentally to your laser thinking, right? Bad has no value. And, we can do something like, let me compute the relative ratio of A to B, the relative improvement of A to B. And if A is 0, I'm going to return an unexpected, and otherwise I'm going to return a computation. And this is an implementation of a symbol function that actually creates unexpected. And then you just propagate it as it goes. Right? Cool. So now if you want to do simply centralized, you simply just convert any expected you have by using operator star, and you just proceed on the happy case. Exceptions will be thrown. You don't care, right? You just use the pointer notation and just move, just simply code for the happy case. And that would be centralized error handling with exceptions. The code is similar to the classic code. You just have to have like the stars here and there. That's pretty much what you need to do. Using our previous example, you say double, not unexpected. You say double growth equals relative on 1 to x, and you just put a star here and we're good. An exception would be thrown. Separate the normal path from the error path, so that's great. And just like with exception, just add the star there and you're good. All right, so now we have the local case, and in that case, we simply test if it has an error. So we say if not R, then we're going to do the local error handling, and everything is going to be fine without actually any exception being thrown, just construct and destroy it. Much cheaper, right? Actually, I have another idea which I want to email Jean-Francois about, which is sometimes you don't even want to construct the exception. You want to construct lazily, and you want to throw even lazier. And to construct lazily ideas, thoughts. How do you, in C++, how do you do lazy evaluation, lazy computation? Use a lambda. So how about instead of having a union with 2 fields, well, 3 is a crowd, right? So instead of a union with 2 arms, which is like normal case exception, maybe I have a third case, which is a functor, a lambda, which is supposed to create the exception should I ever need it, right? That's pretty awesome, right? It's pretty cool, and that would be pretty useful, and I think very economical in many cases, because again, that's only on the unhappy case. And unless you have a lot of context from which you want to create the exception, that may be a lot smaller too. So I mean, just the same size actually, so not much bigger. So that would be really nice. And it's general enough, we don't have any more issues, no special values, no nothing. So we're good. Pretty awesome. And there's one more interesting artifact of this way of doing things, which is you may have an error, like in that joke, I was walking through a forest and the tree fell in front of me, I couldn't hear it. Right? So it may happen that you walk in the forest, an error does happen, but you never need a value. So the error never manifests itself. By the way, should something happen or not? What's your opinion about this? So again, the error did happen. So, the conversion, something failed in the system, but you never look for the normal value, for the happy case. Should something happen, should an exception be thrown or not? By round of applause, who's with yes, please, throw me that exception. All right, who's with the uncaught thief is a good, honest man? Who's with the decibels here? Like, who can measure the... All right, so actually I've been through a number of opinions. Like in the morning I would wake up like, that we should throw there. And then the next morning I'd be... So I think what happens right now in the proposal is no exception is going to be thrown. The tree will not be audible in the forest, right? And I think that's the right approach, because it really means something did happen, but you weren't needing it. So if I wouldn't need it, why would it be thrown in my face, right? So that kind of stuff. So this is lowercase z, by the way. All right, so no harm done. So this is great. Another question that was, okay, what if I have an expected of void and something? Expected void or something. Should it be allowed by round of applause? Should I have expected void? All right, measure. All right. Should I not have expected void? Should it not compile? I swear to you, it's the same people. The same folks. Those guys I paid. I'm going to applaud. Whatever the hell he says, I'm going to applaud. He paid me. So he gave me $50, you know. All right. So this is actually an active discussion right now. So should we, like, what does it even mean to have expected void? Because it means it's pure side effects, in which case, why would you ever need the exception lazily, and what would happen, and, you know, what happens in this case? Because in this case, there's no way to actually test the object, right? There's no, you know, it's kind of a weird situation, right? In my opinion, you know, I think excepted void should be either disallowed or given a complete special status, which means maybe the destructor could throw an exception. Don't shoot, don't kill me, no. All right, so it's kind of an open discussion right now. It's an interesting one too. By the way, you get to influence it. You just Google for, you know, C++ expect, and you're going to find a proposal. You're going to find, actually, wait, look on my Wikipedia page, right? And you're going to see this guy, all he did was this expected thing, right? He was expected to do it anyway, so that's all he did. This is awesome. So, you know, get from there and get into the discussion with the authors and see how it goes. You get to influence the process. This is the time. So, checkpoint. With expected, we associate errors with the computations, and that's great. It's like pretty much like associating like mutex with data. It's like, you know, the same idea. You associate the error, you know, what you want to build with what could happen while you build it. So that's a pretty awesome thing. They're like, this is really top 10 in my, you know, on my list of good things about expected is this one. Naturally allows multiple errors in flight. We discussed this already. Teleportation across time, across threads, across everything is natural and easy. We can collect group and combine errors together. And this is kind of a bit kind of subtle, but it's actually easier for a compiler to optimize. Let me explain. I mentioned already the whole function prologue and epilogue thing. By the way, you know, like compiler implements a function that may throw. So it implements it with goto, like jump. But essentially, the way it goes, did you ever write in C that idiom with like if error go to like the end of the function? If you write 5 more lines and they say, oh, if something has happened, go to like another point toward the end of the function. I see some nods, some sad nods here from you folks. So yeah, indeed, I've seen that. And I've seen shops in which goto is disallowed except if it's used in this manner. So this manner is allowed. Because those people wanted to not have exceptions because they hate them. So they're like goto and then they have the goto. And that's similarly how the compiler implements the whole may throw an exception thing. And the multiple endings of the functions are destructors for the locals in the function, right? So guess what? When you're constrained like that, there's an important optimization that you cannot do anymore as a compiler writer, which is, okay, who can tell this? I'm gonna sign whatever he wants or she wants on the forehead. What? Tail call. That's not what. That's actually good, but yeah, it's a good. Reorder code motion. Thank you. I'm gonna sign it if you want. I don't think you want, but code motion. So the compiler, the important thing they do is they move code around for maximum efficiency, and all of this is severely constrained whenever you may have exceptions because of these restrictions in code generation. So this is important. It's much simpler for a compiler to optimize. Great. So with this, destroy. Thank you. Thank you very much. Thank you. All right. Well, we have like minus 1 minute for questions. There's a question from the back.
Okay. The one thing is not clear. For example, I have a function which I declare as no except to utilize this magnificent way to handle errors. But wouldn't it confuse compiler that if I the reference expected object to access the value, the code has such condition if
Right.
it's okay, then
Right.
access object, if not throw. So I basically throw in no except function. How would compiler handle
Okay.
that?
So let me repeat to make sure I understood. So you say even if I guard, if result is good, right, then use star result. Even if I check,
yeah.
okay. So let me give you some good and bad news at the same time. No except is not checked. It's taken on faith by the compiler from you. So the compiler not only is not going to get confused, it doesn't care. Like, no except, right? No problem. So yeah, it's a good point. If the compiler wanted to do the analysis, it would not be easy. It wouldn't be not
Okay,
trivial.
thanks.
Thank you. Yes. Question in the back. Question in the back. All good people are in the back. Come on, guys. I'm seeing a notepad somewhere.
Hey, I'm here.
Yes.
In the happy path that you presented, the way you're going to use expected, you also check. First you check for expected that exists, and then you dereference it, right?
Right.
But as you showed in the operator star, you also check it for validity, right? So on the happy path, you
here.
check it twice, right?
Here, right?
Yeah.
And
yes.
inside this is going to be another check.
Yes.
Yeah, actually,
Exactly.
you know,
That's not fast enough, Andrei.
it is actually fast enough. It's zero cost because hear me out. These functions are perfect candidates for inlining. And after inlining the double test, I guarantee any optimizer that's any optimizer after 1990 is going to do it. It's going to optimize the second check away. It's really, so this is really like, it's common knowledge by now that the double test after inlining is not done twice. So you can rest assured about that.
Okay, great. Why don't we have the same behavior in STD optional?
STD optional. Does it do some check twice and you notice that in generator code it?
I mean, if you reference STD optional that is null up, then the behavior is undefined, I believe.
Oh, actually, yeah. So behavior is undefined, but that's not a double test. It's a one-time test. They don't want to test even that one because that may be a highly difficult to predict Boolean. But let me put it this way: people changed the design of expected to be more like optional, and I think that's a mistake because I don't think optional is a piece of good design. So you kind of touch a nerve because I don't think optional is an example of good design. And people said, oh, we should make them more like the same. But optional is pre-existing, so you can't change it. And expected sometimes has to do kind of unpleasant things.
Okay, thanks.
Thank you.
Another question about how you implement the swap operation when we have different state, and you created a temporary object of E. Okay.
Right.
Why not temporary object of T? Probably it might be if you have an example expected of int and runtime error, it's much more cheaper to have temporary object of int, not of temporary object of runtime error.
I think that's a great idea, and I also think that in general exceptions must be polymorphic because you want to catch them by reference and kind of call virtual functions. So it's very plausible that the exception is more expensive to construct than the object. So I think it's a great idea, yeah. This is, by the way, it's not the official implementation or anything. It's just a correct implementation given as an example. But I think that's a great idea. Thank you.
Okay, thanks.
All right. So many questions. All right.
Thank you.
Thank you.
If I remember the first implementation of expected used exception pointer, except of using now exception as a template parameter. So what to do if function may throw runtime error or logic error?
What do you do if you get one of several possible exception types? My initial design used the exception pointer, you're right. The currently proposed design uses this. Exception, and the rationale was that exception pointer is really a reference counter smart pointer, which uses dynamic allocation, so it's more expensive. And right now, I don't think there's an easy way to say this may throw that or that. So you're going to have to factor them into the base class, which is std exception. So that's the only way right now.
Okay, and one more question, please. In case that no one cares about returned value, and if we consider that exception should be thrown, how may it be thrown? How it may be thrown if no one checks the result?
Oh, in the destructor, and you would able to only do that if the destructor is no throw, no except, right? So you could do that in certain cases. So that would be kind of a weird. I think nobody's going to accept that because it would create a huge precedent. Oh, now destructors can throw. So wait a second. There's so many things I can do, right? So probably not. Yes, questions. There's one more here. There are a lot of people who they're like, the hell with it, I'm not going to ask anymore. Yes.
I was wondering what you think about using monadic interfaces with something like expected, and would that belong in the standard?
Would monadic interfaces be good? I think that'd be good. And actually, the initial proposal had the monadic interface too. And then some people didn't like the monads, and they said, we're not going to do that. So they rewrote the proposal without the monads, and they plan to, like, once they, it's like in sales, right? First you sell the jacket, and then you sell the pants, right? So they plan to sell the jacket first, and then say, oh, you need some pants with that because this short doesn't look good on you, right? So I think the plan to add monads is a bit deferred right now. But yeah, I think it would be a great idea. Yes, questions? There's somebody there.
Just one comment on the monadic part. I think it's going to come through a small door through coroutines, and that was what I wanted to ask you. So you have a couple of different ways to handle the expected, and with coroutines we're going to get, instead of the star expected, co-await expected, and then just do the happy path in the rest of the...
Right.
Okay. But the question was, why did you say that the expected cannot be saved to a file and then restored at a later point?
I was just saying, all I'm saying is that saving objects to files is a difficult topic in and of itself. It's just, I didn't want to get into that. Yeah, you could, in many cases you can do that, and if you have like your own serialization engine, you can do that, but it's not trivial.
Yeah, okay.
Yeah. Cool. Thank you.
Hi, Andrei. Thanks for the talk. I enjoyed it.
Thank you.
Have you thought about cont'd, particularly for obviously the actual throwing pass you cannot handle, but we could make this work, I think, with cont'd for the local handling part.
Cont'd for the local handling part. I don't think they have anything right now about that, but that would be interesting. That would be definitely something to think about. You may want to just follow up with Jean-Francois and just ask them what's the deal with cont'd. So you want the cont'd to be, the happy path be solvable during compilation, and the exception gets thrown, what should happen?
No, so even exception is thrown, it will not be a constant expression. It will not be a core constant expression.
Oh, okay.
But if you happen to have a function there that returns one of these things, and you can handle it locally in your cont'd function,
oh, I see.
Then
Okay.
you can keep on programming. You don't have to say, well, I have one world for this and one world for these others.
Yeah, so I think that's difficult to handle technically because it requires some control flow. So cool idea. Thank you. All right. Guys, I can do this all night. By the way, so there's something in the back that Sergey told me, like a signing thing, questions and answers, anything you want. Yes?
If there is a plan to make functions which return expected mandatory unthrowable, because the user of this function does not expect exception from there. I mean, from the standard point of view.
I think a lot of interesting things are going to happen once expected is in the standard. And indeed, it sounds like a very nice policy to say this function returns unexpected and is no except, right? Because that's the use case that you care about. But right now, I don't have any explicit plans to do so.
Thank you.
Sorry, guys. Once I literally fell off the screen. It was funny. It's on video. Yes, questions. Okay, so whoever wants to ask questions, I suggest you come to the front so we have like a quicker time.
Thanks.
One more. Okay.
Yeah, one more. What about object construction? Currently, the constructor syntax doesn't allow us to return object. I can make a function to construct object, but this is not really integrated in the language. Have you considered what would happen if we were to construct object with
like this kind of stuff?
I mean, not the expected object. I mean, I want to construct object, but I want to return the constructed object as expected.
Oh, I
value.
see. You want to have a factory function.
I won't have to have no throw object construction.
Okay. So you want to have a factory function that returns unexpected. Yeah. That's a cool idea. I think it's great, and I think it's highly applicable. So you'd have a function that takes whatever arguments and then in place, gives you back an expected object. And the drawback would be that I think you can do it. I think it's not going to be syntactically nice because there's no syntax for constructors, but you can write a factory function that returns that kind of stuff easily. Okay, so great use case. Thank you. All right, questions. Yes, please.
Hello, thank you for the talk. I've been using in my code a similar idiom, like homebrew, like without exceptions, with enums and stuff like that. And I found out that I don't want to split my code into, say, low-level part that constantly checks error, and like high-level code that just don't care and lets like exceptions thrown or errors thrown.
You don't want to do that.
I don't want to do that. Okay. I want to write low-level code the same way, so I just like expect the happy case. And if it doesn't happen, I want it to automatically propagate it upper level. So like if I don't handle that case, I may handle some cases, but like other cases will be handled upwards. In standard, we have future, and future have that semantic. So if you throw anything, it will be recorded in future. Right. Do you know if anything like that is expected to be expected? So like you can just write expected function that returns expected. If you have an exception within that function, it is automatically converted to the expected return.
Thank you. Did you use future or did you write your own type?
No, I wrote my own thing. We don't use exceptions, so it's basically just like.
Cool. Thanks for the experience report.
Do you know if that like any plans for that?
I don't know. Beyond what I described is pretty much what's being proposed. So if you want more, you should actually get into the process. You should contact the proposals. Now is the time. This is like really the right time for this. This is still not 100% stable, so this is the perfect time to. I'm actually happy I'm giving this talk here in Russia because there's a lot of interested people and a lot of excitement and enthusiasm for C++ and C++20. So I think this is really the right time. Just write email to the guys. They're very nice. They're responsive, and they're going to listen to your use case.
Thank you.
Thank you. All right. Last 5 questions.
I see.
Thank you for bringing C++ closer to Rust.
Thank you.
And I have a question. With the adoption of this utility in the standard, will it have any impact on the standard library itself, on the error handling?
I think they want to introduce the facility first and change the signatures later, add signatures later. There's not going to be a change in signatures, right? Because a lot of functions in the standard may, plausibly return expected. But I didn't see in the proposal any thing. I didn't see any section saying, well, assuming expected is going to exist, here are the functions that we could define in terms of expected. There's nothing like that yet.
Okay, thank you.
Thank you. All right, questions. All right, thank you very much, you guys. I'll see you in the back. Thank you.